Okay, we had looked at algorithms for sorting, especially quicksort. The way quicksort worked was you picked a pivot, okay, and compared each element in the array with the pivot and split the array into two parts. Those elements which were less than the pivot and elements which were greater than the pivot. And then you recursed on these two parts, okay, and you recursed on these two parts and recursively sorted them, and this then gave you the sorted order for the entire array. Okay. The time taken by quicksort crucially depends on the position of the pivot in the array. Okay. We would like to pick an element which is the middle of the array, okay, which is called the median. So if we could always pick the median fast, then perhaps we can make quicksort work in n log n time, and that's our goal. Okay, that's the next goal, to see if we can we can, given an array, we can find the median in time linear in the size of the array. Okay. Okay, so let me make a few definitions just to set the ball rolling. Okay, the rank of an element. So the rank of an element is its position in the sorted array. Okay, so given an array and an element, to find the rank of this element, sort the array, and the position of this element in the array is its rank. Okay. We'll assume for simplicity that elements in the array are distinct. Every element is distinct. All algorithms that we'll design will also work when the elements are not distinct, but this is just for simplicity. Okay. Okay, so this is the rank and rank of an element, and the median is an element of rank n by 2. It's a floor of n by 2. Okay, an element of rank floor of n by 2. Okay, our objective is to find the median in an array. Okay, and how fast can we do this? So the problem is this: the input is an array A, and the output is a median. Now clearly this can be done in order n log n time by just sorting the array and picking the middle element, right? Sort the array, pick the middle element, that gives you the median, and sorting takes n log n time. Our objective, of course, is to do this faster. We want to find the median faster. Right? Okay, how does one go about doing this? Can we apply divide and conquer, for instance? Supposing we want to apply divide and conquer, how would we like to divide the array? How do you divide the array? Again, it seems sort of, you think about this and you're up against the wall. Okay. Yeah, so supposing, okay, somehow you can find, let's say not the exact median, but some kind of approximate median. What do I mean by an approximate median? Let's say an element whose rank is greater than n by 4, and so rank of x, and it's greater than n by 4. Let's say greater than or equal to n by 4, less than or equal to 3n by 4. N is the size of the array. So these elements I'll call approximate medians. Okay, they are not quite the middle element, but they roughly sit around the middle element. Supposing you could find, supposing somebody gives you an approximate median, okay, then what can you do? I mean, does this help? Well, it may help. I mean, in the following sense that, so here's my array, okay, I take the array, this is my array A, okay, X is an approx median. Let's not lose focus of our goal, which is to find the exact median, okay. X is an approximate median, and well, you just come to know of it somehow, okay. What you could do is this, you split the array as less than X and greater than X, okay. So here are elements less than X, here are elements greater than X, this is less than X, this is greater than X, okay. Once you do this, you know where the median falls, right? If this is less than n by 2, if the rank of X is less than n by 2, then the median falls on the right, okay. It sits in this portion of the array. On the other hand, if the rank of X is greater than n by 2, okay, then the median falls in the left portion of the array. You know which portion of the array it sits in, okay. So the other good thing about this partitioning is that, see, both these parts have size at least n by 4. The elements which are less than X has size at least n by 4. The elements greater than X have size at least n by 4, okay. So if you can get rid of one part, let's say the smaller part, right, then the bigger part is of size at most 3n by 4, okay. So you have shrunk the size of the array by a constant factor, okay. Does this does this help? Actually it does. Supposing I can find this approximate median in, let's say, linear time somehow, okay, we don't know how that's done. So let's see how much time finding the exact median will take, okay. So what we would like to do is this, we have an array of size n, so let's say the time is Tn, okay. We find the approximate median which takes n time, and then we would like to recurse on a small part, okay. That part has size 3n by 4. Well, there's still a problem which we need to address, but supposing you can do this, okay, then you check that this recurrence gives you order n, okay. You can just open out a few terms here, and you can prove that this in fact is order n, okay. There is a problem. The problem is this, okay, I want to find the median in the big array, right. I somehow get this approximate median in linear time. This we still don't know how this is done, okay. I know that the median is here somewhere, okay. This is the element I want to find, okay. The element could sit here, not exactly in the middle. So what I want to find in this array is not exactly the median, okay. The element that I want to find depends, the rank of the element I want to find depends on the left side of the array, okay. So what I want to find, let's say that the numbers, so let's call these two things, let's say A left and A right, okay. Let's assume that the size of A left is less than n by 2, okay, floor of n by 2. We'll assume this without loss of generality, okay. Now what I want is the median of the entire array, okay. What is its rank in AR, okay. So it is the element that I want. What is the rank in AR, okay. Supposing that rank is R, what I want is R plus 1 plus size of AL should be equal to n by 2, In other words, I want R to be n by 2 minus size of AL minus 1. So R is the rank of the median of A in AR. Okay, the small r is the rank, okay, of the median of A in this array AR. Okay, let me draw a picture and sort of explain this again. Okay, this is A. Okay, supposing this is sorted, here is my middle element. Okay, this is n by 2. Right. Now my element x sits somewhere here. Okay, this is the element x, which is the approximate median, and this portion is AL. Okay, this portion is AR. I mean, this size is AL, this portion is AR. Now the rank of the median is just the rank, is the number of elements in this portion. Okay, what is that? N by 2 minus AL plus 1. Okay, so it's nothing but n by 2 minus size of AL minus 1. So the rank of this element, okay, which is the median, this is the median that we want to find. Okay, so this is the median in A. The rank of this element in AR is this. Okay. So the problem when we recurse, we don't really want the median in A. We are not looking for the median. We are looking for an element of rank this. Okay. We are looking for an element of rank n by 2 minus AL minus 1, and this need not be the middle element in AR. This is the first problem. So when we recurse, we don't really want the, I mean, it's not just the median, but we want an element of some particular rank. Well, why not look for a procedure to find an element of any rank? Okay. So pay careful attention here. This is a very sort of important design principle. We started off with trying to find the median. We tried to find a recursive procedure. Along the way, we have encountered a problem where we actually want to find an element of some other rank, not just rank n by 2, but some other rank. So this seems to be a more general problem. Okay, finding the median is a special case of this problem. Sometimes it's easier to solve a more general problem than a specific problem, and in this case, that's what we'll do. So the problem we would like to tackle is not just finding the median, but finding the element of any rank. Okay, so the input, let me write this problem down. So input is array A and R. The output is an element of rank R in A. Now when R is n by 2, we get the median. So this is a more general problem than the one we started out with, right? And this is what now we would like to solve. The reason this problem came up is that during the recursion, I mean at least the recursion that we tried, we started out with the median, but when we try and get the recursion going, the problem we end up with is this. Okay, so this is the problem we will try and solve. Okay, now you see that there is no problem with the recursion, at least. Okay, so if I find an array A, I start with an array A. Supposing this is still a step which is left undone, I get x, which is an approx median. Okay, I split the array into two parts, AL and AR and X. Okay, I want to find an element of rank R. If R is less than the size of AL, I recurse on AL. If R is greater than size of AL plus X, I recurse on AR. Okay, that's it. That's the algorithm. So as long as I can find the approximate median, I can find an element of any rank. Okay, by this divide and conquer scheme, you can write down the recurrence relation and see that if you can find this approximate median in linear time, then you can find an element of any rank in linear time. Okay. So how do we find the approximate median? Okay, this is seems to be as difficult as finding the exact median or median of any rank. Okay. Yeah, so it is, and the solution that I'm going to present, okay, now is really smart. Okay, so the way you find the approximate median is this. First, take the array A. Okay. So unfortunately, I can't tell you exactly how people came up with this. I'm just going to present the solution to you. Okay. Sometimes you just have to be really clever and come up with a solution. There is no real recipe for finding algorithms all the time. Okay. There are a few general recipes that one follows, but often, you know, these things are so problem dependent that you just have to think about it, and at some point, you know, some light bulb goes off somewhere, and you know, you come up with the algorithm that works. So here's the algorithm that works. So take the array A, split up the elements in the following form. So here's A. I split the elements into groups of 5. So these are 5 elements. Okay. These are the first 5 elements, the next 5 elements, and so on. And I have n by 5 groups. I have n by 5 groups in A, and each of them has 5 elements. Now, find the median of these 5 elements. Okay, this will give me some median y1. This will give me some median y2, and the last one will give me some median y n by 5. Okay, these are medians of the groups. Okay, there are n by 5 groups, each consisting of 5 elements, and this is the median of these groups. Okay, now the approximate median which we'll pull out is the exact median of these n by 5 elements. Okay, the approximate median that will output exact median of these n by 5 elements. So let me repeat this again. You split them into groups of 5. There are n by 5 groups. Okay, for each group you find the median. Okay, y1, y2 up to yn by 5. Okay, each group you find the median. Now you find the exact median of these n by 5 elements, and this is an approximate median. Okay, there are a number of questions. Okay, why should this be an approximate median? That's the first question. Second question, we started off trying to find the exact median. We ended up with trying to find the approximate median, and we are again finding the exact median, right? To find the approximate median, we find these y1 through yn by 5, and again we are finding the exact median. What's going on? Well, the second thing is not so serious, in the sense that initially we started out trying to find the median of n elements. We are now finding the exact median on n by 5 elements. Okay, so the size has reduced, and we can apply we can recurse on this smaller size. Remember, I said if you can solve the problem for a smaller size, you know, you can put the solution back up, right? So the exact median that we want to find among these n by 5 elements, we just do it by recursion. Okay, we just recurse and find the exact median here, and that gives you what we want. Okay, we said we want to find an element of any rank. This is what we want to do. If somehow we can find the approximate median, we are done. To find the approximate median, we have to solve an exact median problem on an input of smaller size. And this can also be done by recursion. Okay, I have to still convince you that the exact median of these n by 5 elements will be an approximate median. Okay, let's see why this is. Okay, to see this, let me arrange these 5 elements in each group in descending order. Okay, so smallest element will be at the bottom, say A11, then the next element A12, then A13, A14, A15. Okay, so all of these I will all of these small groups, let me first write them down in increasing order upwards or decreasing order downwards. The next thing I am going to do is look at these middle elements, the medians of these groups, and I'll write them, okay, in sorted order towards the right. Okay, so A13 will be the smallest element among these medians. Okay, so A13 is less than A23, less than A33, so on, and an by 5, 3. Okay, so this is also part of a group, okay, which I have written in this order. This is A22, okay, this is A21, A24, A25, similarly here, an by 5, 2, n by 5, 1, an by 5, 4, and an by 5, 5. Okay. So the entire array I have written out this way. Well, the last row may not be one of these rows may not have all 5 elements. Okay, but if the size of the array is divisible by 5, all of these columns will have, all of these columns will have 5 elements. Okay, so let me again explain this picture. You first split each of them, okay, into 5 parts. There are n by 5 groups. Okay, now you sort them in increasing order. Okay, look at the middle elements. Okay, sort the middle elements in increasing order, lay them out, and lay out the entire array in this fashion. Okay, so A13 is the smallest element among the middle elements. Okay, it comes in some group. Okay, it may be the 20th group or the 15th group or whatever. Okay, whatever it is, I'll call it A13. Okay, so the first group here I get by taking that part of the array where the middle element was the smallest. When I look at the middle elements, this has to be the smallest. Okay, so then comes the second group, and then the third group, and so on, and this is the last. So I've just arranged the elements of the array this way. Now, what is the median of this portion? Remember that we said that the median of this portion is an approximate median. Okay, median of this middle portion is what we claim to be an approximate median. So what is this middle, what is this? So it sits somewhere in the middle here, right? So it's the way we have written this, it's a n by 10, 3. Okay, that's the element which is the median of this portion. Okay, now how many elements are smaller than this median? Okay, where do you find elements in the array which are smaller than this median? Well, if you look at this middle row, right, everything to the left here is smaller, right. Also, everything down here is also smaller, which means this entire portion consists of elements which are smaller. These are smaller elements. Okay. Similarly, if you look to the right, these are all larger elements, and also if I go right and up, I also get larger elements. This is also larger than this, right. So this portion again consists of larger elements. Okay. This portion consists of larger elements, this portion consists of smaller elements, and you can see that each of these, this portion is at least 1/4. In fact, it's greater. For our purposes, this is at least 1/4 of the entire array. This portion is at least 1/4 of the entire array. Good. That's the reason this is an approximate median. Okay. We've just shown that at least n/4 elements in the array are smaller than this. At least n/4 elements are larger than this. That's why this is an approximate median. And once we have the approximate median, well, we know what to do next, right? We take this approximate median and recurse on these two paths. And I have, well, in a sort of vague disjoint way, I have given you all the ideas needed to design this algorithm to find a median. Okay, let's just put all of this together. Okay, let's just write down each step, put all these steps together, stare at it, and then see if we can analyze it and see what the running time is. Okay, good. So, okay, I'll not be giving you code, but I'll write down each step carefully. Okay, so here goes. I want to find an element of rank R in an array A. Okay, so let's call this find rank. Find element. Okay, let's say R A. Okay, this finds an element of rank R in array A. Okay, now what do we do? Well, the first thing is to somehow get this approximate median. Okay, so for that, well, the first step is this. So partition array, partition A into n/5 groups of size 5. Okay, find the median of each group. Okay, now I want to recurse, right? I want to find the median of these medians. Okay, there are n/5 groups, so there are n/5 elements. Okay, so each group and put them in an array, put them in array B, say. Okay, array B has size n/5. Okay, now I want to find element, essentially I want to find the median in this array. Okay, so find element of rank n/10, okay, in the array B. Okay, this is again recursion. So this portion finds the approximate median. Okay, this, well, this should return an element, right? So call this x. So this returns x. Okay, this element x is returned by this call. and this x is the approximate median that we want. Okay, now what do we do? Well, we use, this is something we have done before, we use x, partition array into two parts and then recurse on the right part. Okay, that's it. So partition A into AL and AR. Okay, so elements in AN are less than x, elements in AR are greater than x. Okay, that's how you get AL and AR. Okay, now let's see. So now we are left with cases. Okay, depending on what the rank of x is, we have to either recurse on AL or AR. Okay, so there are three cases. The first case is if x luckily happens to be the element we are looking for. Okay. So when does that happen? So if size of AL is, let's say, n by 2 minus 1, then return x. X is the median that we are looking for. Okay. Now if oh, I'm sorry. So size of AL should be R minus 1. Okay, we are looking for an element of rank R. Yeah, so yeah, if you go back here, what we want to find is an element of rank R in A, not just the median, right? Okay, so if size of AL is R minus 1, then rank of X is nothing but R. Okay, so X is the element of rank R and we return X. So if size of AL, okay, is greater than R minus 1, okay, then we know that this element of rank R sits in array AL, right? The element of rank R sits in array AL, so we recurse on AL. So we say find element okay, so we want still to find an element of rank R and we now recurse on AL. Okay, an element of rank R in AL will also be an element of rank R in A. Okay, that's easy to see. Okay, and the last case is when size of AL is small. Okay, the last case is size of AL is smaller than R minus 1. Okay, then we need to find an element of rank. Yeah, so here's a, let's quickly draw a picture to find this out. So here is X, okay, this is AL, and I know that R is somewhere here. This is what I want. Okay, now this is R. Okay, there are R elements here, there are size of AL elements here, and one element here. So the rank of this element in this portion of the array is nothing but this distance. Okay, that is nothing but R minus size of AL minus 1. Okay, this entire distance is R, this distance is size of AL, and X is just one element. Okay, so we want to find now an element, so find element. The rank is R minus size of AL minus 1, and we want to do this in AR. Okay, this portion of the array, that portion of the array is AR. Okay, that's it. That ends the description of the algorithm. So let's look at this algorithm again. Okay, we want to find an element of rank R in array A. Okay, partition A into n by 5 groups of size 5. Okay, find the median of each group. Now find the median of these medians. Okay, this returns an element x which will be an approximate median, and we are now going to partition with respect to x. Okay, so partition A into AL and AR with respect to x. These are elements smaller than x and those larger than x. And now we are going to recurse on one of these two paths. Okay, that depends on the rank of this element x. Okay, the rank of this element x is nothing but size of AL plus 1, right? So if the rank of element x is R, exactly R, then we return x as the answer. Okay, if the rank of element is x is larger than R, okay, that means the element we are looking for is on the left half of the array. So we just find an element of rank R in the left half of the array. If this doesn't work, well, the element that we are looking for lies on the right half of the array, and well, this is what we do. If the rank is less than R minus 1, then we find an element of rank R minus AL minus 1 in the right half of the array. This is it. This is the entire procedure. How do we analyze this? Okay, we have to analyze this procedure. Okay, so we've seen reasons why this this procedure works. Why we expect that this procedure should run in linear time. Okay, our expectation is that this procedure runs in linear time, and we'll see why this procedure actually works in linear time. Okay, so once you have designed an algorithm, how do you analyze? See, the easiest way to do it is write down the algorithm. Okay, write down perhaps code for the algorithm. Look at each step and figure out how many times each step is executed. Okay, now the step could be a recursive step. So here is, let's say, you have written an algorithm. Okay, for some problem. Okay, there are many steps. One of them could be recursive. Okay, so this is an algorithm, call it A. So you recurse on A with smaller input. Okay, and then there is a loop maybe, and there are steps inside the loop. Okay, this is your normal structure of a program. To analyze this, you need to find out how many times is each step executed. Okay, those outside a loop are executed once. That's fine. For the recursive call, you need to estimate the size of this input. Okay. So for instance, if initially the input size were n, and this is let's say n by 10. Okay, this could be n by 10, and now you have these things in a loop, let's say, and you have to find out how many times each of them is executed. Okay. Now supposing there are 5 steps here, and each is executed n times. Okay, then the total time that you will take, Tn, is, well, Tn by 10. That comes from the recursive step, and the total time is 5 times n. There are 5 steps, each takes n time, right? Each of them is executed n times, and that gives you phi n. So we are going to do something similar to our algorithm, right? For the median, let's look at these each of these steps, and we'll see how much time each of them takes. Okay, so T of n is the time taken on an array of size n. So we are going to write a recurrence for T of n. Okay, so let's look at the first slide. Okay, partition A into n by 5 groups of size 5. How much time does this take? Nothing. Okay, this partition is easily done. Find the median of each group. How much time does this take? Well, each of those 5 elements, each of those n by 5 groups, I could even sort. Okay, that will take, let's say 25 sort of comparisons for each group. I mean, even if I do bubble sort, and there are n by 5 such groups, so it's some constant times n, right? So this step, finding the median of each group, takes constant times n for the entire array. So let me write this down. So this is the first step to the cost. Okay, C1 times n. Okay, this is to find the median of these groups, of each group. There are n by 5 groups. For each of them I spend some constant time, right? And that gives me a total of C1 times n. Okay, what about this? What about this step? Well, I recurse on something of size n by 10. Okay. So, sorry, I recurse on B. Okay, this is the rank I want to find. I recurse on B, and B has size n by 5, right? So I recurse on a problem of size n by 5, so that's Tn by 5. Okay, plus. Okay, now, okay, we get here, we partition this into 2 parts. So how much time does this take? This takes n time, because each element is compared with x. Good. So this takes an additional n. Okay, this is to partition this array into 2 parts once we find this x. Good. Okay, after we do this partitioning, now we recurse. Well, if we are in this case, we are done, we return. If you are in this case, or if you are in the next case, we recurse on a smaller part of the array, right? So we recurse on either AL or we recurse on AR, depending on where this, what was the rank, what was R and what was the rank of X. We either recurse on AL or we recurse on AR. Now we know, so this is the last step, okay? So that's what I need to write. So this T of something, this is the recurrence. So what do I put here? Well, both AL and AR, notice the size of AL I know is at least n by 4, right? Size of AR I know is at least n by 4. Now this implies that size of AL is less than or equal to 3n by 4. Why is this? This is because size of AR is at least n by 4. So size of AL is at most 3n by 4. Similarly, size of AR is at most 3n by 4. Right? So whichever side I recurse, the size, the maximum size it can be is 3n by 4. Okay, so I can put 3n by 4 and I put less than or equal to. What I put here, the size, can only be less than or equal to 3n by 4. So the maximum size an array can have when I do this recursion is 3n by 4. So the recurrence equation I get is this: Tn is less than or equal to C1n. This is to find the median of those 5 of these groups, n by 5 groups. Here is a recursion to find the exact median. Okay, this is the time for partitioning, and this is the last recursion. We recurse either on AL or AR, and the maximum size of AL and AR is 3n by 4. Okay, so this is the recurrence. Okay, so so Tn is less than or equal to let's say C1 plus 1 n plus T of n by 5 plus T of 3n by 4. Good. So what is the solution to this recurrence? That's what we want to see. Okay. Okay, so here is something I want to sort of share with you. So look at the recurrence. Okay, look at where we recurs. One is a problem of size n by 5. Okay, this is a problem of size n by 5. The other is a problem of size 3n by 4. Now the sum of these two is less than n. Okay, n by 5 plus 3n by 4 is strictly less than n. Good. In such cases, usually you will end up with something which is linear. Okay, so let's try and prove this. So we know, and in such cases, instead of writing down this recurrence the way we've been doing, there's an easier way to do this. Okay, so I'll assume that Tn is less than or equal to Cn. I want to prove this. Right? So I want to prove this. So let's just substitute this into the previous equation and see what we get. So I get Tn. Okay, so let me just do this on a new sheet. I know this Tn is less than or equal to C1 plus 1 n plus T n by 5 plus T 3n by 4, and I want Tn is less than or equal to Cn. I want to find a right constant here, C. Okay, so let's just plug this into the original thing. I get Tn is less than or equal to C1 plus 1 n plus, well, Cn by 5, okay, by plugging in Cn, plus 3 by 4 times Cn. Okay. Now, if this is less than or equal to Cn, if I can find C so that this is less than or equal to Cn, then we are done. If this is true, we are done. Okay, because we can actually prove this by induction. Even if you don't understand why we are done at this point, we would like to find a C which satisfies this. Okay, so let us find that. So we want C1 plus 1 n plus this less than or equal to Cn. So n cancels from these. So I want C1 plus 1 less than or equal to C minus C by 5 minus 3C by 4. Okay. Okay, so we want C1 plus 1 at most C minus C by 5 minus 3C by 4. So this will imply the previous statement. Okay, and just simplifying this is nothing but C by 20. Okay, C times 1 by 20. So as long as C is at least 20 times C1 plus 1, we are done. So if C is greater than or equal to 20 times C1 plus 1, we see that this quantity is less than or equal to Cn. Okay, so we can choose C to be 20 C1 plus 1. Good. So now it looks like Tn is less than or equal to 20 times C1 plus 1 times n. Right. So this is a constant. This is a constant C. This now we can prove by induction on n. Okay, that Tn is less than or equal to this C times n. We can prove now by induction on n. For n equals 2, it is true because you make just one comparison. And for the inductive step, okay, for the inductive step, we just observe that Tn by the recurrence is at most C1 plus 1 n plus Tn by 5 plus 3n by 4, and now I can use induction. Okay, so Tn by 5 is at most Cn by 5, and this is at most this much. And the way we have chosen C, this sum is at most Cn. Okay, so the proof now follows by induction. In fact, initially we guessed that Tn is at most C times n, and the plan was to use induction. Okay, somehow use induction and prove this, and you just follow your nose with the induction, substitute C and find out what is the C that helps you finish the inductive proof. Okay, so this is the other way of solving recurrence relations. If you can guess the answer somehow, then you know that you want to prove this by induction. So try proving it by induction and come up with the right constants. Okay, and then you can once you found it, once you plug it in and find out what and figure out what constants to use, then you can write the whole thing by induction. Okay, so this proves that the time taken by our algorithm is in fact linear in n. So you can find the median in time which is linear in the size of the array. If you use this algorithm with quicksort, then the worst case time for quicksort would be n log n, but that is if you pick the pivot as a median each time. Okay, the normal way you do it, of course, it turns out to be order n squared.